Okay, thank you. Appreciate the opportunity to go right after lunch. And when I write such a long introduction, I should have just said, I'm Bronwyn's dad. And that would be probably much better. Following Olaf and Chuck Cullum and Frozen is a real tough act to follow. So I'll say that my daughter Bronwyn was actually in Frozen on Broadway when it shut down. So there's the connection, but today you've got me and it's going to be death by PowerPoint, or we'll try and not make it death by PowerPoint. Anyway, I'm talking about drought in the Colorado River Basin, which we've heard a fair bit about. So we've seen the map of the watershed, that it's supplying water for 40 million people, supporting $1.4 trillion of annual economic production. So that's actually something, maybe it could pay back the national debt in a few years. And we have the iconic threatened ecosystems. And we've seen the declining natural stream flow at Lee's Ferry with the millennium drought towards the end of that period. And those two bars in blue are the sort of estimates, the provisional data. That's the natural flows estimated by reclamation. Yes, which way to? So the key points I want to cover is what to expect this year, how dry might future conditions of the Colorado watershed become, and then we can look at past flows reconstructed from tree rings or future flows projected from climate models. Both indicate that there are droughts more severe than the current drought that we're in. So that's tells us to actually be careful about what's coming up, and then climate change is impacting things even more. And then there's also the question of changing watersheds. So at the end, I'll introduce how do land cover changes, forest disturbance affect hydrology, and how is the land cover changing, and connect that to some interesting work that's been done by Sarah Goking, who's working on a PhD with me and about to defend in a couple of weeks. So we've seen a slide like this of the snowpack. This happens to be the one that shows all the SNOTEL stations in the upper Colorado River Basin. And you can see that we sort of peaked at something less than the median, and it started to decline. Right now, it's averaging out at about 13.7 inches, and then this is just a simple average of the actual 104 stations that are in there. One has to think about their positioning and how representative they are if you want to get real estimates of the actual snow, but this is what's really available. If you look back at past years, last year was 13.8, and if we've peaked out at that, it's slightly worse than last year. The previous year was 16.8, and the median typical peak is about 15.5. So what is that actually going to mean in terms of stream flow? So we've seen information similar to this, but in this graph, I put the last 30 years or so of data, and I'm showing what's the natural inflow or the natural flow of the Colorado estimated at Lee's Ferry. So that's the measured flow, but putting back in the estimate of consumptive uses and everything that reclamation takes for in that account. We also heard from Chuck Cullum mention of unregulated inflow. So that's the inflow to Lake Powell if you take back out what reservoir operations there are, but has the consumptive uses in the upper Colorado Basin already taken out of them. So there's a difference between those two lines on average of about 3.85 million acre feet per year. And I guess just like Jack apologizing for the units that the Colorado's run on acre feet. And then the bars on the different axis indicates the peak snow water equivalent from those 104 stations from the previous slide. So you can see, unsurprisingly, that there's a fairly good relationship between the snow water equivalent and the inflows. So that's a good thing. That gives us some level of predictability at at a simple level. So this is just a sort of aggregate type of prediction. Hydrologists at the Colorado Basin River Forecast Center and the National Water Center are running really sophisticated models to try and do more detailed predictions. But there's a simple sort of regression that would tell you how the peak snow water equivalent natural inflow. And there's also been some comments on efficiency. What's the ratio of the natural flow to peak snow water equivalent, and not worrying about the sort of units differences in there. Looking at when that ratio is high, then we talk about an efficient runoff. More of the snow is turning into stream flow. When that's down, there's an inefficient runoff. And we see it goes up. There's where it's up. There's some low years down. The last couple of years, it's been really low. The number's about 0.5. And that's related to soil moisture. And there have been a few indications that maybe soil moisture is not quite as low this year as it was last year. But if we were to predict what's going to happen and we assume the similar efficiency, it would not necessarily bode very well. So in terms of where we stand for predictions of the flow this year, Reclamation made a forecast on the 15th of March that was sort of 10.4 million acre feet natural flow, and they put a range on that. And that was using the ensemble approach. And I think that actually derived information from the Colorado Basin River Forecast Center. Then if you just use this regression line, you would get something comparable. But if you said the efficiency was going to be about the same, you would get a similar natural flow to last year, which is about 6.8. So we could be in for something equally as dire as last year, which, given how low the reservoirs are, isn't necessarily very good. So that's sort of my look at where we sort of currently stand with perhaps inflows to Lake Powell and what might happen in the current season. But I want to really take a longer view. So here we're looking at the natural flow at Lee's Ferry, and on this graph, I've got this sort of red line that's kind of faint to see that goes up, and then the 10-year red moving average. That's the observed natural flow at Lee's Ferry, but many researchers, and I've picked data from Dave Miko, have looked at tree ring reconstructions that go back to the 1400. There are tree ring reconstructions that go back even further, but this is one of the ones that Miko reported was the most skillful, so I decided to use that one. And you can see there's a pretty tight relationship between the reconstructed flow and the observed flow for the period that overlaps. So let's look at some periods in this. So over the observed period of record, the mean is about 14.6. I think this is one of the numbers that Jack pointed to earlier. If you exclude the early 20th century pluvial period, you get a mean of 13.84. If you look at the millennium drought, as we're referring to it, from 2000 to 2021, you get a mean of about 12.3. And if you go look at the worst tree ring drought, so that's this one over there, you've got 11.7 million acre feet. So there have been worse droughts in the tree ring record than there are historically. And the point is, if it's happened in the past, it could happen again. So we should at least be planning for that. If we look ahead towards climate change, there's a lot of people who are running climate models, and we did an analysis where we picked from climate models that other people ran, the CMIP5 data set. We found 10 that seemed to match reasonably well to representing current droughts, and looked at the average of those. And they're giving a relatively high flow. Wouldn't it be wonderful if we got back up there? There's a lot of uncertainty in climate models, so but that's just at least what they're coming up with. So I'm going to be using what we refer to as a duration severity analysis to try and understand some of the flow variability. And in this top graph here, I've got the flow versus time. And we're going to identify drought scenarios based on averaging. So we take durations in years and look at the average over those durations. So, for example, the lowest year on record, 1976, would get plotted down there as the lowest mean flow with a 1-year duration. You can look at, find the 5-year block that has the lowest mean average, and that happens to be this block from about 2000 to 2005 or 2000 to 2004. You can look at find the 12 years that have the lowest average. So what we're effectively getting is this sort of distribution going up here, where these dots show the mean flow associated with a particular duration. So it's combining the severity of the drought represented by a mean flow and the duration. And we're going to be coming back to sort of this type of plot to try and understand our data in the interplay between drought severity and duration. So that first lot was for just the lowest set of flows. You can also then look at what's the second lowest flow associated with each duration. So these are the blue points over here. So that corresponds to that period and so on. And then you can do it effectively for all the data. So look at the full set of dots for all the durations. So here I've taken the historic flow measured at Lees Ferry, 1906 to 2018. This plot was produced before we had 19, 20, and 21. You can see associated with a duration 1, each dot effectively represents a year's flow. Duration 2, each dot represents a 2-year average. Duration 3, each dot represents a 3-year average. So you see that the lowest 1-year flow was 5.4. There was a 5-year period with an average of 9.47. And you can get it down here to a 19-year average with a flow of 12.44. And if you look at the complete set of data, the average is 14.76. Coloring in red all the years post-2000, you see these, and you see that they've clustered down to the bottom of the graph. So that's showing that the sort of post-2000 period is one of the lowest. So we're sort of using this perspective to evaluate drought scenarios that we're going to be simulating. So the present millennium drought is characterized by a sustained 19-year average of 2.3 million acre-feet below the long-term mean. So given the fact that society has come to depend on the long-term mean, the full 15 million acre-feet of consumption that Jack mentioned, it's no wonder that reservoirs are dry or getting there. You can then do the same thing for the tree ring record. And so we see, again, sort of lowest 1, 2, 5, out to 25 years. And one of the points to note is there was a 25-year sustained drought with average flow well, that was the average flow I had in the table earlier, below the long-term mean. And you can see that the post-2000 period doesn't correspond to the worst in the tree rings. And you can identify in this where the sort of worst sustained droughts are. You see here 1576, 1579, 1579, 1579. So these are all data points that are from that single period starting 1579 that had the worst drought in the tree ring record. So tree ring droughts more severe than the historic droughts have happened before and may happen again as the sort of take-home point from that. So with that perspective, we wanted to provide simulations that could be used to help plan for what future droughts might be. And we identified 3 periods to look at. One is the current drought that we're in. One is the mid-20th century drought. And then this tree ring drought that started in 1576. And we developed a procedure where we would just pick those years and then effectively randomly resample from them. So setting aside all of the wet periods, because we wanted to be really focusing on situations that are going to sort of stress the system, because we think that that's what actually has to be planned for. We generate streamflow traces by sampling at random to make them sort of representative of the past, but different from it. And then we used a disaggregation approach to sort of spread it out to each of the inputs of a model, and then use that to evaluate what the model gives using the Colorado River system simulation model. So this is what you get if you do those simulations, and you can look at the lowest duration severity results. And now if you do that 100 times, you've got 100 scenarios. So that's what each of the sort of gray dots and lines are. And then you can sort of put bands on that. So the lowest, the 10th to the 90th percentile, and the median. So that's showing effectively how duration and severity is interacting. And you can then compare those simulations to the actual data by putting it back on the same dotty plot. So this shows just here the millennium drought scenario, and on top of the tree ring data and the historic data, and I offset it just a little bit to separate the dots. And the take home from this is that the millennium drought simulations are severe, but plausible when considered in the context of the historical tree ring scenarios. So that's effectively justifying these simulations as something plausible to use in planning. We can also do it for all three of the scenarios and do the same thing. And we found that the most severe tree ring simulations are more severe than have been observed, at least even in the tree ring simulations, but they are plausible because they're based on past individual years. So then if you put that into the Colorado River system simulation, and you operate it according to the current rules, the current law of the river, you find, and here I've just plotted in terms of the distribution of Lake Powell's elevation, you find that you've got considerable periods represented by sort of all the part to the right of the line where the lines intersect, where Lake Powell would fall below the intakes to the power plant, and that's really indicating a need to rethink the management and operation, which really comes down to figuring out a way to reduce the use, because we've got inflows that are averaging about 12.5 million acre feet, but the uses are about 15, and the uses are sort of baked into this model, and it goes lower than the levels unless use is reduced. So then we stepped back a little bit and looked at some of the other things that are going on in the basin. And if we look at trends in temperature, we find it's getting warmer throughout the basin, and that shouldn't necessarily be a surprise. We also wanted to look at forest disturbance. And if you look at the data from the forest inventory analysis, you can see that there's a lot of the basin is colored red here. And that means that the change in live biomass has decreased. The change in dead biomass has increased. The reds indicate an increase here. There are places where the dead biomass has reduced. So we are seeing changes in vegetation, disturbance due to all sorts of things, bark beetle infestations, fires. This is a combination of everything as done from the Forest Service's inventory analysis. Then working with Sarah Goking, we looked at, okay, so what does this mean for the hydrology? So each dot here represents one watershed from the CAMELS set of watersheds, which is a set of watersheds collected by or established by some other hydrologists to look at sort of long-term trends. And we juxtaposed the trends in hydrology as looking at the runoff ratio, stream flow divided by precipitation, relative to tree growth, whether the trees are increasing or decreasing. And the sort of common rule that you expect is if there's more vegetation, there's more evapotranspiration, less stream flow. So positive tree growth should be a decrease in that. But if you've got the trees being disturbed, you would get an increase in stream flow. We're finding a lot of places where the opposite actually holds. And Sarah wrote a beautiful review paper about it. And now this is the paper that's submitted to Water Resources Research that's describing looking at this large sample analysis. But the point is that there's negative tree growth is associated with decreasing runoff ratio in some of our most arid parts of the watershed, down in southern Arizona, a few in Utah as well. So when you look at data some more, you can see that I guess here we're finding that in the more arid watersheds, where there's a large mortality, the runoff is decreasing. So tree mortality is associated with declining stream flow in the most arid watersheds. And those are the ones that the forests are really vulnerable. And I've been told my time is up. I'll just point out that soil moisture is also part of the story. And we heard a bit about Park Williams' paper, and there's research on runoff efficiency. But the points I wanted to leave you with is we seem to be in a period of aridification, perhaps a new normal, and we should expect and plan for lower flows to match supply. Past droughts provide plausible forecasts. And then when you look at the scenarios developed to use as input to CRSS, you get considerable periods when lake levels get low and you need to rethink management. We've got climate change, as well as tree mortality, and future forecasts need to combine the effects of climate and vegetation change. So I think there's some important things there, and I'll be happy to answer any questions.